Unit 2.2, we've titled Properties from Algebra. We call these properties of equality. Properties of equality. They're in my Algebra 1 book from page 28 to 29a, if you'd like to look there and get more examples. Page 28 to 29a in the Algebra book. Again, it can be found at www.dballardproductions.com. All right, properties of equality, the addition property of equality. What we're going to do is we're going to give it to you in the proper algebraic form, and then we're going to show you how to use it in an algebraic example and how to use it in a geometrical example. And eventually we'll use a lot of these in proof, algebraic proof, and in the middle of some geometrical proof. Now, addition property of equality says if A is equal to B and C is equal to D, then A plus C is equal to B plus D. Now, that sounds like gibberish when you first hear it. But let's analyze this a little bit closer. What it really says, if A is equal to B, that's one statement. And this gets to be important when we're doing proofs. How many statements are in the addition property of equality? 1, 2, 3. The first statement says if A is equal to B, see that's given, and C is equal to D, that's also given, then we can reach this conclusion, and the conclusion by addition is that the sum of these two, A plus C, is equal to the sum of these two, B plus D. If A equal B and C equal D, then A plus C equal B plus D. We used this in algebra when we were going to add something of equal value to each side. When we did this in algebra, what we added to each side was generally the same thing. Here's the way we would have said it in algebra. We would have said, okay, if I have x minus 3 is equal to 7, and I want to solve for x, then I would need to undo subtraction by addition. So what I would need to do is add 3 to both sides to balance my equation. But before we can add something to equal side, we have to know it's equal. And so we basically have the statement in our head. That's a fact. We know that 3 is equal to itself. But see, this is actually the A and B, if A equal B. And this is the C and D. C is equal to D. That's the 3 is equal to itself. Then if we add this side and get x and add that side and get 10, then this right here is the sum of A and C, and this right here is the sum of B and D. So we use the addition property of equality when we undid subtraction by addition, as we called it in Algebra 1. If you look at page 29a in the Algebra 1 text, then you can see a good explanation of how we used addition, subtraction, multiplication, and division properties of equality to solve. And you can see those same examples here under the subtraction, multiplication, and division almost, okay? Now, this is a little bit more of a complicated version here. This is basically a logical proof with basic numbers. If 3 is equal to 1 plus 2, which we know it is, and 9 is equal to 5 plus 4, then we could reach the conclusion that 3 plus 9 is equal to 1 plus 2 plus 5 plus 4, and you could verify that obviously, see? Okay? Now, in a geometrical standpoint, we may not be adding numbers, we may be adding segments, or we may be adding angles. We've learned about segment addition, recall, and we've learned about angle addition. And so in the process of taking big angles and turning them into little, we could use subtraction. Or in the process of taking little segments and turning them into big, we could use addition. Example, if this little segment here, AB, is equal to this little segment, DE, that's this given statement, and this little segment, BC, is equal to this little segment, EF, then the sum of these two, which is AC by segment addition, is equal to the sum of these two, DF by segment addition. Now, this is kind of tricky a little bit, I guess. The thing that says that the sum of these two little pieces here is equal to this whole thing AC is segment addition. The thing that says the sum of these two little pieces is equal to the whole thing DF is segment addition. But the thing that says if I take this little piece equal this little piece, and this little piece equal this little piece, then whole thing is equal to whole thing is addition property of equality. See, segment addition says little piece plus little piece equal whole thing. Addition property of equality says if A equal B and C equal D, then A plus C equal B plus D. Okay? So segment addition allowed us to say AB plus BC is AC. BDE plus EF is DF. That's segment addition. All right. Subtraction. Same as addition, except we're subtracting. If A equal B and C equal D, then A minus C equal B minus D. And again, it might be better or easier to see this vertically if A equal B and C equal D, then A minus C, the left side subtracted, would be equal to B minus D, the right side subtracted. And again, what we're doing is subtracting something of equal value from each side. Now, in an algebraic setting, that's usually the same thing as in this example, where we would undo addition by subtraction. We would subtract 4 from both sides and get x is equal to 8. If we had to give a reason in a proof for this conclusion, we would say subtraction property of equality. And we'd probably put a T R so as not to confuse it with substitution. Okay? So before we can say subtraction property of equality, we have to have 3 statements. See, there's 3 statements that lead up to the conclusion subtraction property of equality. That's important as we lead into proofs. Now let's look at this situation. If angle ABD, that's this whole big angle, is equal to angle EBC, that's this whole big angle, then what could we conclude? Well, since this big angle, they both contain angle 1, then we could subtract angle 1 from both of them since they both contain it. By angle subtraction, we really have angle addition, but you realize if you've got angle addition, you can say angle subtraction. So if we subtracted that little angle, that green one out, we would get that this angle right here is equal to this angle right here, right? If the whole big angles are equal and we take an equal chunk out of both, then what's left is equal. So our conclusion would be that the little angle here, angle ABE, is equal to the little angle here, angle CBD. Now, what tells me that this angle ABD minus angle 1 is equal to angle ABE is called angle subtraction. What tells me that this big angle EBC minus angle 1 is equal to this little angle is angle subtraction. But this whole thing together, if this big angle equal big angle and little angle equal little angle, then little angle equal little angle, the whole thing, if A equal B and C equal D, then A minus C equal B minus D, that whole concept altogether is the subtraction property of equality. Okay? We just used angle addition to actually do the subtraction part. All right. Multiplication says if A equal B, then AC is equal to BC. We just multiplied them both by the same number. Now, multiplying by the same number has lots of implications in algebra and geometry. First of all, mathematically, to solve, we would undo division by multiplication, and we would actually show our work like this, recall. We would undo division by multiplication, and we would see that those reduce to ones, and we would get x is equal to 72. With that conclusion, we could reach based on the multiplication property of equality. We undid multiplication by division. Again, you can see that property on page 29A. Now, the concept of undoing, in case you're a little bit unfamiliar with that and my terminology, you can see the concept of undoing in this text on page 25 and 26. And then we get to these properties, which you may think is out of order, but I like to discover things sometimes before I present them, which again may be considered backwards in your mind. But anyway, the undoing process is page 25 and 26, and the properties of equality that really tell us we can are page 28, 29A. Um, when you look at a common thing you multiply by, the multiplier is called a factor. And when we think about factor, then our mind goes to scale factor. And when it goes to scale factor, it goes to dimensional analysis, similar figures, and all kinds of stuff. Okay? So it just kind of opens up a whole lot of things as we start thinking about a factor, a scale factor, similar triangles, dilating, scaling up, scaling down, and all those things associated. Division, if A equal B, then A divided by C is equal to B divided by C. In other words, we can divide both sides by the same thing, but we learned that division by 0 is mathematically undefined. We actually discovered it in the Algebra 1 textbook on page 96, examples 7 and 8, where we began to look at horizontal and vertical lines and discovering zero slopes and undefined slopes, and we said that the slope of a horizontal line was 0. The slope of a vertical line is undefined because division by 0 is mathematically undefined. So here we need the disclaimer that C can't be 0. Algebraically, to solve here, we would undo multiplication by division, the result being x is equal to 3. And the reason, if we had to give one in a proof, division property of equality. Notice again, and this becomes important, that it takes 1, 2, 3 statements for us to have the division property of equality. Therefore, we'd have to have at least 3 statements before we could use that reason, okay, in a proof. Now, we use substitution all through Algebra 1 because to solve a system, one of the methods was to solve by substitution. So we would take what y is equal to and put it in place of y to solve for x. That substitution method is substitution in the algebra book is page 29, and then we began to talk about substitution on page 42 and the substitution property of equality in the algebra text. I'm sorry, the substitution method of solving a system in the algebra text is page 142. So if you want to see some more real-life application of substitution, there's some good places to look, and that would be a good place to review your Algebra 1. If A equal B, then A may be replaced by B in any equation or inequality. If two things are equal, this is what it says in my algebra book on page 29 at the bottom. If two things are equal, then one may be replaced by the other in any equation or inequality. An algebraic example may be where we're trying to prove that angle A is equal to 90 degrees. And we may have the statement that angle A is equal to angle B, and then the statement that angle A plus angle B is equal to 180. Now, if angle A is equal to angle B, then I could replace the angle B with angle A. So in this second equation, since angle B is equal to angle A, I can replace this angle B with angle A and have angle A plus angle A is equal to 180 degrees. Or I could have written that as 2 times angle A is equal to 180 degrees. The reason I can make this statement is substitution. Property of equality. This statement would be given, because it said if, which is given, and this statement would be given, and then the conclusion, angle A plus angle A equal 180, would be from the substitution property of equality. We replaced angle B with angle A because they were equal. I'm going to kind of clean some of this out. We could take this even farther and keep the algebra moving, and we then could say angle A is equal to 90 and give a reason. And if you think about it, the reason would be we undid multiplication by division, right? If we wanted to make the statement right in the middle of this, that 2 is equal to 2, that would be reflexive property. You may recall that from Algebra 1. And then the conclusion that angle A is equal to 90 came from dividing both sides by 2. And so that is a result of the division property of equality. And so we've done a whole proof. We've got an algebraic equation where we've solved all the way down to angle A equal 90, and we justified every single step with the property of equality. Okay? So that's kind of where we're headed with this. The symmetric property, or transitive property, I whited it out, and I like to skip it. It's a good thing I moved the screen. It reappeared on me. If A equal B, now notice I better color code this different. If A, I lost my pen works. I'm back here. If A is equal to B and B is equal to C, then A is equal to C. And in the algebra book, we called this, it was transitive, but when I taught it, we called it the transfer policy, transitive transfer. A is transferring through B to C, so the conclusion is that A is equal to C. If A equal B and B equal C, A equals C. This transitive property could also be used for angles. If angle 1 is equal to angle 2 and angle 2 is equal to angle 3, then we can transfer from 1 through 2 to 3 and reach the conclusion that angle 1 is equal to angle 3 by transitive property. Likewise, we could transfer through more than one thing. If 1 equal 2 and 2 equal 3 and 3 equal 4, then we can go from 1 2 through 2 through 3 all the way to 4 and conclude that angle 1 is equal to angle 4 by transitive property. At some point in this text, we will begin to talk about parallel lines, and we'll talk about vertical angles, and we'll learn that angle 1 is equal to angle 2 because vertical angles are equal. And we'll learn that angle 2 is equal to angle 3 because alternate interior angles are equal. And we can then also say that angle 3 is equal to angle 4 because vertical angles are equal. And then we notice that we can transfer from 1 through 2, 3, through 3 to 4, and also reach the conclusion that angle 1 is equal to angle 4 by substitution. So our reason here, which we've not learned yet, would be vertical angles are equal, shortened down. Our reason here would be because the lines are parallel, then alternate interior angles are equal. We would have to first be given that they're parallel, and that's what those arrows mean. We could say that angle 3 is equal to angle 4 because vertical angles are equal. And then once we knew all of that, we could reach the conclusion that angle 1 is equal to angle 4 by, the transitive property. We transferred from 1 through 2 through 3 all the way to 4. I started writing substitution because really you can see that transitive is a lot of substituting. If 1 equal 2, we could put the 1 where the 2 is, and that would become an angle 1. If 1 equal 3, then we could put 1 where 3 is, and that would become an angle 1. So what transitive really is a bunch of substituting. The 1 went to the 2, to the 3, and finally was associated with the 4. Okay? Any questions on that? Symmetric, you flip the equation around. If A equal B, then B equal A. If A equal B, then B equal A. That becomes important sometimes when we're doing proofs and we're trying to line up our angles and stuff. And if we want something on the left or instead of the right, we could switch it over so things just kind of line up prettier. When we're doing that, if A equal B and C equal D and all that, it may be that the wrong one's on the wrong side, so we turn our C equal D into D equal C in reality, right? Switch those. Okay, so that'll be important sometimes to do. Reflexive is equal to itself. A equal A. Angle 1 is equal to angle 1. In the subtraction example, and I'll just make one up here, let's say that we had x plus 4 is equal to 9. Now, we could say, well, that's the given equation. And I want to solve for x, and I would undo addition by subtraction, so I would subtract 4 from both sides. But the addition property of equality says if A is equal to B and C is equal to D. So by the subtraction property of equality, we really need to make the statement that negative 4 is equal to negative 4. And the reason we can say that is reflexive. Now, what we're really just trying to do is show our work, but there has to be a property or a rule that says that that's true, you see. And then we would reach the conclusion that that subtracted is equal to the right side subtracted, and so that is a result of the subtraction property of equality. And I probably will abbreviate subtraction SUB, and if I'm going to abbreviate substitution, I'll put SUBST for substitution. Okay? Distributive property in the Algebra 1 textbook is on page 31, and it's a real important part of solving equations. On page 33 is the whole order of operations horseshoe, and part of it says, see if there's anything you can do to simplify in the order. Please excuse my dear Aunt Sally looking for distributive property and combining like terms. We needed that. Distributive property summed up is page 171 of the algebra text, and it tells us that you can only distribute onto a one lesser operation. And we get very specific in those videos about substitution. And then page 200 is where we're multiplying two binomials, and some people use what's called the FOIL method, if you speak less country than I do. But anyway, uh, what I use is the order of operations, and so I call it fancy distributive property. And if you watch that video on that particular lesson, that would be lesson 7.2 in the algebra text, and you can kind of see a little bit more about how I teach distributive. Now, what distributive is you're going to take the thing outside and multiply it by the two things on the inside. And so we will have A times the first little piece B, and then A times the second piece C. And so we would have AB plus AC. Now, let's look at some examples of distributive. If we had 3x squared times 5x to the third y minus 6xy to the fourth, here's how I actually present it there. We say, okay, what are the operations we're dealing with? And the operations are multiplication and parenthesis. So we would say, well, order of operations says to do what's in the parenthesis first, and there's subtraction. So we say, well, can you subtract those? Well, no, they're not like terms. So you can't subtract, so you can't do what's in the parenthesis. And so you go to the next operation, multiplication. And the way I teach it is that operation, multiplication, is crammed on a parenthesis. And since it's crammed on a parenthesis, we check for distributive property. And on page 171 of this text, we explained it this way. We said you can only distribute onto a one lesser operation. So we said, what does multiplication distribute onto? Well, it distributes onto addition or subtraction. That is subtraction, so that gave us permission to distribute. Well, we're actually multiplying, and so we learned on page 5 of the text a little jingle of the Algebra 1 text, and that is to multiply the numbers. 3 times 5 is 15, and you multiply the names and you get a new name. And when you multiply with like bases, x's with x's, you add the exponents. Remember that, x to the fifth. And then this y didn't have a partner here, so you just cram it on. And then we're going to multiply, and we don't forget our sign rules. Sign rules are on page 18 of the algebra text. So when you multiply with different signs, the answer is negative, so we put a minus 18. And then when you multiply with like bases, x's with x's, you add the exponents, and there's a 2 here, but on there there's an understood 1, so that would give us x to the third. And then y doesn't have a partner over here, so we would just have y to the fourth. The operation left is subtraction, and you can't subtract because they're not like terms. We looked at a distributive property problem like that. We also learned how to distribute division, especially as we went from standard form of a line to slope-intercept form of a line on page 107, which is a very important part of algebra. And then on page 171, we learned to distribute an exponent over multiplication and division, and that got a little bit complex. So those are some places that if you want to take another look at distributive property, you can. All right, let's look at some examples here. It says state the property or postulate represented by each. Now remember that the if part is the given. So in other words, we're saying given that this is true, the then part is called the conclusion, right? What allows me to conclude that this is true? Well, algebraically, we went from a 6x to an x, and so that 6 disappeared. The 6 was being multiplied, and the thing that would make that go away would be division. If you divided, you would get an x there, and over here you would get a 2. So we got x equal 2. That is a result of having divided both sides by 6, and so we say that it is a result of the division property of equality. Any questions on number 1? How did we go from the if statement to the then statement? Okay? All right, there's lots of things here. We're going to have to leave some for you. Let's just do number 8. I was trying to choose there. There was a little bit of silence. I was trying to choose between number 4 and number 8. There's some similarity with those, but I decided we'd just go ahead and look at number 8. Number 8 is given if given that angle AEC is angle DEB. And when it does that, you really should draw those in the picture so you can see it. Remember, if you get stuck in the mud, you put it in four-wheel drive in your truck. If you're stuck in geometry, you draw a picture. So angle AEC, that big angle, is equal to angle DEB, this big angle. We started out with big angle is equal to big angle. And the result we're trying to get to is angle AEB, that's this little angle, is equal to angle DEC, that's this little angle. Little. And I'm writing big, little for a reason. Sometimes students aren't able to see what's going on, but if we just think logically instead of at the algebraic or geometrical pictures, in other words, take our mind off of the math application and just use common sense, then we can see we went from something big to something little. Now, there's only, if we look at the order of operations, please excuse my dear Aunt Sally, if we're going from something big to something little, we're generally either dividing or subtracting, correct? So we either took something away or we cut something into chunks. Well, if you look at the situation, then what you would see is that that angle is a part of the red angle and it's a part of the blue angle. And if we took it away from both, you would end up with those little pieces. So if from this red angle AEC, I took away that black angle BEC, I would end up with the little green angle, angle AEB. See that? If I started out with that big blue angle, DEB, and I took away that same black angle, angle BEC, it would leave me with the other little green angle, angle DEC. So I must have subtracted angle BEC from the two big ones to get the two little ones. So I can justify that statement with the reason, subtraction, property of equality. Now that's the whole thing. Just this side is angle subtraction. Just that side is angle subtraction. The whole thing, if A equal B and C equal D, then A minus C equal B minus D is subtraction property of equality. Any questions on that? Okay. Now I want to talk about number 10, and we're going to leave some of these for you, but I want to talk about number 10 because it seems that lots of people struggle with that. It says if angle 1 is equal to angle 2, that's one given statement, given that this is true, and also given that this is true. What allows us to reach the conclusion that this is true? Now, what you might do if you get kind of stuck is to just kind of compare. Well, which one of the two ifs givens looks most like the conclusion? Obviously, this one. From here over to here is exactly the same. Plus angle 6 equals 70. We say, well, they sure do look a whole lot alike, but what is it that makes them different? And as we investigate what makes them different, it's the fact that in this one there's an angle 1, and in this one there's an angle 2. And the only way that could happen is if we replace the angle 1 with the angle 2. And to be able to replace angle 1 with angle 2, we have to know they're equal. If they are equal, then I can take what angle 1 is equal to, angle 2, and put it in its place. And if I did, I would end up with the second statement, or with the conclusion. So I can reach the conclusion that angle 2 plus angle 6 is equal to 170 because I put angle 2 in place of angle 1 to get that substitution. And again, you may be reminded on page 42, we began to use substitution to solve. Page 142 was the substitution method of solving systems, and so we've used that all the way through Algebra 1. Any questions on the properties of equality? You may have noticed in some of these lessons, I'm doing the lesson and the practice together, the daily work together. And that's because they're kind of short and you really don't get the lesson down good until you go over some of the homework with it. So I'm teaching some of these together. Appreciate your watching the videos. Hope it helps.